Hello everyone, welcome to a very important section of the revision series in organic chemistry in Chemistry by ANR. We are going to deal with mechanism of organic reactions. Often children panic when they go to write mechanism because they don't know where to give arrows, why to give arrows. So let us understand them, let us revise them rather one by one. So here we can see SN1 reaction. SN1 reaction is a substitution reaction, nucleophilic substitution, unimolecular. That is, rate of the reaction is dependent on the substrate Rx only. The mechanism involves two steps. The first step is the slow RDS and is the reversible step where protonation, or rather not, where self-ionization takes place. And this is said to follow first order kinetics. That is, rate of the reaction is dependent or is proportional to the molar concentration of substrate Rx. So here is one example, CH3 whole thrice CBr in presence of OH minus. So this OH minus can be generated from aqueous, KOH, NaOH, anything you take aqueous, polar medium will generate OH minus faster. And you will get retention in configuration in SN1 because where the Br was oriented, there only the OH is oriented right now. Now the step 1, this is the mechanism where the step 1 includes self-ionization. CBr bond breaks in presence of a polar protic solvent. So this CBr bond breaks where the carbon was having sp3 hybridization and the structure was tetrahedral. So this is the slowest step and this is the rate determining step. So in this step there is carbocation formation, and in the carbocation formation the carbon is sp2 hybridized with a planar structure. So the stability of the carbocation will actually affect the rate of the reaction. Step 2 includes nucleophilic attack over the carbon positive center, which is the electrophilic center, and it is a fast step. And so after the attack there is retention in configuration. The term retention in configuration means OH is aligned to the same side as the leaving group. Br was the leaving group, so there is no change in the configuration, there is retention in configuration. So now here we can see that 1 degree allylic or benzylic halides, why I have given this separately is the rate of the reaction actually depends on some factors like the stability of the carbocation being the most prominent factor, because in the slow RDS you have the carbocation getting formed, so the carbocation should be stable. So generally we see a 3 degree carbocation is more stable than 2 degree, is more stable than 1 degree, but under certain circumstances a 1 degree carbocation of allylic and benzylic is getting greater reactivity than that of a 1 degree RX. Why? Because these carbocations are getting extra stability on account of resonating structures. So these are the resonating forms of allylic and benzylic. First one is allylic, the second one is benzylic carbocation respectively, like this. So this is how you can draw the structures, the resonating structures of allylic carbocation, benzylic carbocation. In case of allylic, we can see we are getting equivalent resonating forms. So next, now if I start with optically active substrate, here we can see it was not optically active, right? When I am taking CH3 whole thrice CBr, this one is not chiral, this is a chiral substrate. Now, if I take chiral substrate, optically active means the substrate needs to be chiral. So let me see that. If I take chiral substrate, here we are. This is our chiral substrate because this carbon atom is bonded to 4 different groups and hence it is chiral, and the molecule itself is chiral, for which this is considered to be optically active. Now, the step 1 again includes self-ionization, and you are getting a carbocation which is sp2 hybridized. And now when aqueous KOH is given in presence of OH minus, which is the nucleophile can attack the carbocation center from above the plane also, below the plane also, because this is sp2 having a planar form. So when it is having a planar form, then this can attack above the plane also, below the plane also. Now you cannot show it in a better manner rather than showing it from left side and right side in a 2D. So now you attach OH first on a side which was having Br, there only OH is attached, and to a rear side, to the opposite side which is having Br, because both are equally probable. And these two forms are known as enantiomeric forms. They are enantiomers, where one is D and the other is L, or one is having optical rotation of plus sign and the other minus sign, and they are in equal proportion, for which it forms a racemic mixture. Why equal proportion? The reason is the probability of OH minus to attack from above the plane and below the plane remains same. So the proportion of both the forms, retention in configuration and inversion in configuration, is same, equimolar. Rate of the reaction depends on first type of solvent, as I said, because the solvent needs to break the CX bond, so it is favorable for a polar protic solvent. Why? Because it involves the breaking of the CX bond by solvation of the halide ion with the proton which is present in the protic solvent. Protic solvent means it has the proton. So this presence of this proton, presence of this polar nature facilitates the breaking of the CX bond. Next, type of substrate RX. Here the substrate needs to provide a more stable carbocation. So a 3 degree is greater than 2 degree is greater than 1 degree, or I can say a 3 degree is greater than 2 degree is greater than, say, allylic or benzylic 1 degree. This is primary and is greater than any other 1 degree Rx, because we have seen this allylic and benzylic carbocations are resonance stabilized. It is also dependent on the type of the halogen, because Ri greater than Rbr greater than Rcl, because the leaving character of I minus is greater than that of Br minus is greater than that of Cl minus. Again, if anyone is asking you why is it so, because carbon to I bond is easily broken. The bond enthalpy is less than that of CBr is less than that of CCl. So this is the ease with which the bond is broken, and hence the ease with which X minus is getting generated or liberated. Moving on to SN2 reaction, which is a substitution nucleophilic bimolecular following second order kinetics. And it is a single step reaction. Since it is following a second order kinetics, we can say rate of the reaction is proportional to Rx also, nucleophile also. So the rate of the reaction depends on Rx molar concentration as well as the nucleophile. So now I can see Here, this is Rx, CH3X, carbon is having sp3 hybridization, it is tetrahedral structure. OH minus is attacking from the rear side of X minus, rear side of X, because this is having a delta negative polarity. So if it attacks from the side where X is there, there will be repulsion. So in order to minimize the repulsion, the nucleophile is taking maximum distance from X. So it is a backside or rear side attack, and the attack of the nucleophile over the electropositive or over the electrophilic carbon and the leaving of the leaving group both takes place simultaneously. So this is a single step reaction. It is a single step reaction, though two arrows are shown just to show you what is happening in between, or to show you what is happening during the attack. During the attack, you can see these two ends, delta negative, are at maximum distance to each other in order to minimize the repulsion. So this bond is getting broken and this bond is getting made. So this is bond making and the other is bond breaking. Carbon halogen bond breaking, carbon to OH bond making. Now here inversion in configuration occurs just because it is a rear side attack and X minus is leaving. So this is the stereochemistry of the reaction. So rate of the reaction depends basically on the type of Rx, and so here why? Because since it is a rear side attack, now the less sterically hindered substrate will give a better rate. So 1 degree greater than 2 degree greater than 3 degree Rx is the rate of the reaction. Now, since carbon to halogen bond is breaking, now the bond enthalpy will decide the leaving character. So I minus is greater than Br minus is greater than Cl minus. Moving on to next mechanism, beta elimination reaction, which is also known as dehydrohalogenation. Dehydrohalogenation means removal of hydrogen and halogen, or removal of HX minus HX. How? In presence of alcoholic KOH, which is acting as a base. Please mark that if I take aqueous KOH, then the substitution reaction was the major reaction that was taking place, and you were getting alcohol because you were getting OH minus ion readily on account of the polar nature of the medium. But if I take alcoholic KOH, it acts as a base, and you know all bases are nucleophiles and vice versa. That means if there is substitution, there will be elimination. If there is elimination, there will be substitution. Now it depends on several factors which one will be the major or most probable pathway. So one of it I said is the solvent. If I take aqueous medium, the substitution product will be the major product. If I take alcoholic medium, the elimination product will be the major product, because KOH in alcoholic medium acts as a better base. Now, this is beta elimination. The carbon atom having the halogen is alpha. The directly attached carbon to alpha is beta. The protons which are attached to beta are acidic in nature. These are acidic protons on account of the polar nature of CBr bond. So, for that reason, this H is abstracted by the base, forming a double bond, and Br minus leaving simultaneously. All these take place simultaneously. The base is abstracting proton, formation of double bond, Br minus leaving. So, you get a double bond between alpha and the beta carbon, and you get alkene plus KBr plus H2O, since I have taken KOH. Now keep in mind that if I have more than one type, not more than one, but more than one type of beta hydrogen, then more than one alkene will be formed. So how do I know how many alkene will be formed? Simply see how many types of beta hydrogen are there. As many types of beta hydrogen are there, that many alkene will be formed, with the most substituted alkene as the major product as per Sadzev's rule. Some of the book may show you ZSAF as well, but as per Sadzev's rule, you can say that the most substituted alkene is the major product. So this is one example which I have given you to show you there are two types of beta hydrogen, and hence I am going to get two alkenes by the elimination of alpha from alpha carbon Br and from beta 1 H once, giving a double bond between alpha and beta 1, and again between alpha and beta 2. Now out of these two, the first one, you just see the C double bonded C system has 2 hydrogen. Here the C double bonded in the second one C system has 3 hydrogen. So obviously the first one is the most substituted alkene and first one is the major product. Now this is another question from NCERT exercise. NBuBr plus KCN in presence of ETOH H2O forms NBuCN. You are supposed to write the mechanism. Now, please mention that NBuBr is 1 degree alkyl halide. Since it is 1 degree alkyl halide, the most probable pathway is SN2 pathway because it follows the pathway where the steric hindrance is minimum or less. Now, Cn minus is generated, which is an ambident nucleophile. This is an ambident nucleophile, but the carbon-carbon bond is stronger than that of carbon-nitrogen bond. These all information also we need. So Cn minus is attacking the carbon which is delta positive and Br minus is leaving, and this takes place simultaneously in a single step and it's SN2, and so you get the transition state which cannot be isolated. It is very much higher in energy. There is a difference between transition state and intermediate. Intermediate has a lower energy than transition state. You can isolate the intermediate, but transition state cannot be isolated because this is a state which shows the stage of bond making and bond breaking. So the CBr bond is getting broken and CCN bond is getting made. So you can mention it, and dotted line means something is happening. It's the transition state. Either a bond is getting made, formed, or it is getting broken. So now in the product, since the attack is from the rear side, you are showing back side or rear side attack. Cn is attached from the rear side and there is an inversion in configuration. So the structure gets inverted. Do form the bond between carbon and carbon because carbon-carbon bond is stronger than carbon-nitrogen bond. So this is being mentioned here. Next, acid catalyzed dehydration of alcohol. Alcohol, one example I have given, this is ethanol. So, dehydration means removal of H2O. Acid catalyzed means acid is acting as the catalyst. In presence of H+, the acid which is generating the H+, alcohol gets protonated. So step 1 is protonation to form protonated alcohol, which is known as oxonium ion. So this oxonium ion has, you should see that there were 2 lone pairs above oxygen. It uses 1 lone pair to hold H+, left over is another lone pair. So this is oxonium ion. Now here in step 2 there is dehydration and formation of the carbocation, and so this is your slow RDS, rate determining step. After the formation, so obviously the rate of the reaction will depend on the stability of the carbocation. Now after this you have dehydration, that's why you are getting only the carbocation, and the positive charge over carbon will not remain because H2O is there in the medium. It acts as a base abstracting the proton. It's amphoteric in nature. So it abstracts the H plus also and it forms a double bond. So here we can see a double bond getting formed. So basically we can see that there is removal of OH from alpha and H from beta, and it is alpha beta elimination of OH and H in order to get an unsaturated compound, getting unsaturation between the alpha and the beta carbon. Here again, as many types of beta hydrogen, that many alkenes will be formed with the most substituted alkene as the major product. So this is another mechanism I have given. Butanol getting protonated, forming oxonium ion, getting dehydrated, minus H2O to give you the carbocation intermediate. This is the slow RDS, but the carbocation is 1 degree. So if you get 1 degree carbocation, and if there is a scope of increasing the stability of the carbocation, do so. So here we can see that if there is a 1,2 hydride shift, then the 1 degree carbocation can actually generate a 2 degree one, which is more stable. So both the carbocations will give you the final product, but obviously the more stable carbocation will give you the major product. So we have deprotonation from the carbon which is attached directly to the positive carbon. So you are getting two alkenes. The one with the major product is from the more stable carbocation. So next we can go to the next mechanism, formation of ethers from alcohol. Now alcohol dehydration gives alkene. We have seen that occurs at a temperature say 443 Kelvin, and here at 413 Kelvin we get ether. So since dehydration of alcohol gives alkene also as and ethers also at two different temperature. One is 413 Kelvin, the other is 443 Kelvin. So where the heat is required in order to obtain alkene, and the other one it is forming ether. So this is it is forming ether. So we can see the mechanism over here that ROH can abstract proton. First is the protonation. So it's a reversible step. On protonation, you get protonated alcohol, which is again known as oxonium ion. The other mole of ROH is acting as the nucleophile, and it is attacking the delta positive carbon and giving H2O. So it is dehydration. So here this is the slow RDS. What is happening over here is nucleophilic attack is taking place and dehydration is also taking place. So I can say this is SN2 type reaction. So where the nucleophilic attack is taking place, this carbon should be less hindered. So obviously this will be preferable if it is a 1 degree than a 2 degree or 3 degree, because the reaction mechanism is SN2 type. So it is nucleophilic attack by alcohol followed by elimination of H2O or dehydration. Now you have to do deprotonation in order to get the final ether. So this is how ether is obtained from alcohol. Next, reaction of ether with HX, and we generally write reaction of ethers with HI because I minus is a better nucleophile again. Now let us see the example with unsymmetrical ether where I am taking CH3O, CH2, CH3. So this part is a bulkier part having more number of carbon atom. So this is reacting with HI. The first step is protonation step. Oxygen abstracts the H plus with the help of the lone pair. One lone pair is left and oxygen gets a positive charge. So step 1, protonation plus I minus, because here from HI, I minus is getting eliminated. So now in the next step, we are seeing that it is SN2 reaction where the nucleophile I minus is attacking the carbon which has lower number, the side which is having lower number of carbon atom, because this is less hindered. So since it is having less number of carbon atoms, so this is less hindered and this side it will attack. So I minus attacks here and another mole of alcohol is getting formed. So CH3I and CH3CH2OH is getting formed. If excess of HI is used, then only this alcohol will again get protonated to form oxonium ion. Then only again I minus will attack here and water will be eliminated, dehydration, and you get finally CH3CH2I. So it depends, if there is excess of HI then you will get this. So first is protonation, formation of this thing, ether gets protonated. Only if it is alcohol then only oxonium ion. This is not called oxonium ion, it's protonated ether just. After this there is nucleophilic attack, which is the SN2 type, and this is your slow RDS of the reaction, and you get one alkyl halide. The alkyl halide where you have less number of carbon atom, which is less hindered, and the other one is alcohol. If excess of HI is there, then the alcohol gets protonated and dehydrated, followed by the attack of the nucleophile I minus. So this is the final product. Next, if I have a 3-degree carbon on the side attached to oxygen, one side is 3-degree, then the reaction pathway changes. It is no more SN2 type, because for a 3-degree SN2 type will be more sterically hindered. So first step will be protonation. So step 1 protonation, followed by step 2, which is the slow RDS, carbocation formation. After the carbocation formation there is I minus attack, and here always remember the I minus attaches to the 3-degree carbon, because the reaction pathway has changed and it has gone through formation of carbocation intermediate. So if there is excess of HI, then only CH3OH will again get protonated and dehydrated to form CH3I plus H2O. Next, the reaction with a benzylic position getting attached to oxygen. Here again always keep in mind, like a 3-degree one, the reaction pathway again changes to form a stable carbocation, which is resonance stabilized benzylic carbocation, followed by I minus attack and CH3OH formation. This CH3OH can again react with HI to give you these set of products. So this is how the reaction is. Now you may also have questions like anisole. This is OCH3. So this is anisole. And the question is, if I give HI, then what products do I expect? Don't even think about breaking the bond between carbon and oxygen, this the one which is attached to the benzene ring, because it has partial double bond character. So always think that this bond will break and there will be X attached to carbon and oxygen side has I. So oxygen side has H because HX addition. So you will get phenol, and you will get CH3I, or I can write in general CH3X. But like the other cases where alcohol was again reacting, if excess of HI is there, phenol will not react with excess of HI. The reason is the carbon and oxygen bond has a partial double bond character and it will not break easily. Next, hydration of alkene. alkenes get hydrated in acidic medium. So it is acid catalyzed hydration in order to form alcohols. So let us see what is happening. H2O abstracts H plus to form H3O plus, which is the electrophile. So this is the generation of the electrophile followed by electrophilic addition. This electrophile is abstracted by the pi cloud of the alkene, and the proton getting abstracted, you get CH2 plus and CH3. Now this center is electrophilic center where the nucleophile H2O can attack. So here what is happening is the carbocation what you are getting formation step 1 is your slow RDS because there is formation of carbocation, and to that carbocation H2O is attacking. So oxygen attacks with its lone pair and gets a positive charge, and in the final step there is deprotonation because H2O can take H plus and neutralize the charge over oxygen, forming alcohol. So this is the mechanism of formation of ethanol from ethene, which is very frequently asked in board exam. Or maybe the mechanism is given, the arrows are also given. You are supposed to find where there is any error and rectify the error. So nucleophilic addition of carbonyl compounds. Carbonyl compounds are susceptible to nucleophilic addition because of the polar nature of CO bond. The carbonyl carbon is electrophilic in nature. It has a delta positive character and oxygen has delta negative character. So the carbon end is the Lewis acid end and the oxygen end is the Lewis base end. Now in step 1, that is only the slow RDS, nucleophile is attacking the electrophilic carbon, oxygen forming O minus. So you can see a change from sp2 hybridization to sp3 hybridization. Oxygen with the negative sign in the step 2 gets protonated and forms OH, which is the adduct over here, addition product, because the double bond is no more there and there is a carbon to nucleophile bond formation. Now this addition product can be obtained with HCN where you are getting a cyanohydrin. So HCN will generate the CN minus nucleophile with the help of a base, because the base abstracts the proton and there is generation of CN minus, and this CN minus will act as a nucleophile and can form a cyanohydrin with carbonyl compounds. So here we can see that since carbonyl compounds are susceptible to nucleophilic addition reaction, out of aldehyde and ketone, which is more susceptible to nucleophilic addition reaction? For that we need to know that what are the factors on which this nucleophilic addition reaction depends. One is the delta positive character, that is the electronic factor. So based on the electronic factor we can say that the greater the delta positive character of carbonyl carbon, so greater is the rate of the reaction, that is electrophilicity over the carbonyl carbon should be greater. If I say ketone, then in ketone the delta positive character of carbon is less. Why? Because in ketone there are alkyl groups that are actually having plus I effect. On account of the plus I effect, it reduces the delta positive character over the carbonyl carbon and thus reduces its electrophilicity. The second factor is steric factor, that is steric hindrance to nucleophilic attack. Nucleophile is attacking the electrophilic site, delta positive carbon, that is the carbonyl carbon. So if we consider ketone, it has alkyl groups, minimum one carbon atom methyl also has a greater steric hindrance or produces greater steric hindrance in comparison to aldehyde. So considering these two factors, chapters, nucleophilic addition for aldehydes are greater in rate than that of ketone. That also, if I consider aliphatic and aromatic, aliphatic aldehydes are having greater rate to nucleophilic addition than aromatic aldehydes and then ketone. So that's all for the mechanism part in the revision series. I hope the revision series is useful for you.